Great.
Sorry. Hello, everybody. I am David Mateus. I'm originally from Bogota, Colombia. Right now, I'm living in Grand Forks, North Dakota. Currently, I'm doing my master's in space studies in the University of North Dakota, and I'm a master's candidate at the Universidad Nacional de Colombia. This was part of the research that I did for my first master's. The co-author of this presentation is Jorge Sofrony Esmeral. He's a professor of the Universidad Nacional de Colombia. As you can see, the name of this presentation is Modeling of a Positioning System for Astronauts on Mars. Okay. On Earth, there are three navigation satellite systems as GPS, that is the most used around the world, GLONASS, that is a Russian global navigation satellite system, and Galileo, that is a European global navigation satellite system, and that is getting popular nowadays. And China is creating a new one that is that the name is Beidou. I think that right now it's working just in China. It's not a global navigation system. But before the creation of global navigation satellite systems, our ancestors used to use stars to navigate through the seas or to travel great distance. In the case, in this case, the stars functioned as global navigation systems reference, since they are observable through the planet. Later, they started to use the compass as and started to use the Earth magnetic field as an additional global reference. Due to the cost of sending satellites to Mars, it will be very expensive to launch a cluster to develop a global navigation system on Mars. With all of this, it's necessary that the first Martians, explorers or humans, have an independent navigation system that works by recognizing environmental variables in the same way that our ancestors did, taking into account that Mars has a celestial sphere very similar to a terrestrial one, but doesn't have a magnetic field. Okay. So, as you know, we already have robots or rovers on the surface of Mars. Yeah, these rovers already use navigation systems, global navigation systems, integrating inertial navigation systems. These ones basically are gyroscopes and accelerometers that works with the gravity. Yeah, the gravity is a global reference, as always is pointing to the same direction. They also use celestial navigation systems and visual navigation systems. Just the inertial navigation systems and the celestial navigation systems are global navigation systems, because the last one use a local reference as, I don't know, a rock, features in the on the landscape. Yeah, but the inertial navigation system use the gravity, that is a global reference, and the celestial navigation system use the stars, that also is also a global reference. Okay, as I said before, Mars doesn't have a magnetic field, so we just have the stars and the gravity as global positioning reference. Gyroscopes that are part of the inertial navigation systems work with the angle of roll and the angle of pitch, because the gravity is perpendicular to them. On Earth, for the angle of geo, we use the magnetometers. But as we don't have a magnetic field on Mars, we can't use them. So we saw that the main problem for navigation systems on Mars is the yaw angle that, seen from a global reference, is the same of the azimuth, right? Sorry. Okay. Also, as a requirements, we are taking into account that the sensor that we are going to use as is going to take one of the reference that are the stars, need to be in an area of the spacesuit of the astronauts where the view is not compromised by any part of the spacesuit. So probably this part of the spacesuit is going to be the helm. And finally, another requirement is that we need to design the sensor with commercially off-the-shelf devices, due to it's necessary to start to work in tools for astronauts that are easy to reply on Mars, because as you know, it's so too difficult to start to send new devices because it's so expensive. So for this, we use NVIDIA Jetson Nano, that is a powerful computer for developers for application of image classification, object detection, segmentations, because it has integrated a GPU. We also use an astrophotography camera and an IMU, commercial one, that has gyroscopes and accelerometers. Okay. Probably I haven't talked a lot of this, but to design the sensor, we need to do a sensor function. With other navigation systems, we can function accelerometers, gyroscopes, and magnetometers. Here we can do that for the angle of pitch and roll, but we can do it for the angle of yaw. For the angle of yaw, we are planning to integrate the accelerometers, as the accelerometers don't need a global reference, and a celestial navigation system that at the beginning we talk about them. So for this celestial navigation system that we want to create, or that we already create, we are gonna create a software based on an algorithm or two algorithms. The first one is servo, that is an algorithm that calculates the points of interest in an image. Also, we use the other one, that is another algorithm that is named FLAN, that is a matcher. So what it does, basically, it takes two images that were processed before with servo. So we already calculate the points of interest, and after this we match the features of both image. These algorithms are in the OpenCV library. That is a library that works with C++ and Python. Basically, it has it's used for computer vision and has a lot of algorithms, and two of them are the ones that we are going to use. Okay, as we are gonna use sensory integration or sensor fusion, the way to do this is through a Kalman filter. So basically, the Kalman filter is a linear quadratic estimation. So for this, we create or we designed a model for the system. This is the model of the system in states of variables of state, and where x, the xt is the system state vector, ut is the input vector at time t, a, b, and c are the system matrices, and omega t and vt, or omega t and vt plus 1 are the errors. Omega t is the measurement error or noise, and BT is BT is the measurement error, and omega t is the process error. Okay, and Kalman Filter has two stages, one of prediction and one of update. So through a Kalman Filter, we take the measurements of the accelerometer, and in the case of the roll and pitch, the, the accelerometer and the gyroscope. And the case of the angle of yaw, we use the accelerometer and the celestial positioning system. So through a Kalman filter, taking into account the previous measurements, it decides which of the two measurements it's gonna take. It do some calculations and has at the end the result of that is an accurate measurement of the fusion of both sensors. So for the text to test this implementation, we did a static test. This test seeks to determine the noise level associated with the sensor. We just expose the camera to 20 different stars patterns and take 200 measurements on each of these patterns, since the sensor will be in a completely static position. It is taking the real value of the comparison in 0 degrees for the azimuth and the zenith. So here we are taking the bias error of the sensor and the implementation, finding the average of all of the measurements of the 200 measurements that we did.
Hi, David. You have 10 minutes remaining.
Okay, thank you. And also we did a dynamic test where we start to move the pattern. So with this, we measure the precision and accuracy, taking into account that in this case we are simulating the movement of the stars. So for this test, we take a base pattern, and by moving this pattern a certain number of pixels, the movement of the pattern is reflected by the change of the angle. Yeah, as we have said, we are trying to measure the change of the yaw angle. So these displacements describe that. So this was a test that we did in a laboratory. So we use just a screen and the camera, and we determine the pixel displacement as as an angle displacement, we did this calculation. So at the end, the displacement in 1 pixel corresponded to 0.02 degrees. So after this test, we have the results. Actually, the camera, just the camera by itself worked really good. We just have like errors of less than 0.01 degrees, and after the sensory fusion, we have just we have the half of the error. So in both ways, worked really well. So thank you so much.